So we're going to take a look at the last 2 pages of section 3.3. And so just as a reminder, this is section 3.3, and we're on page 41. And so this last example is, I guess you could call it a more applied example. And this is coming straight from the book, the example that's given in the book on page 291. So I strongly encourage you to check out that example. It's in the in the text, so you can take a look at that. We're basically given a differential equation, a system of differential equations in matrix form that represents the daily profits of a coffee and a tea shop. So the coffee is X and the tea shop is represented by the variable Y. So since we're talking daily profits, these would be in units of dollars, right? So both X and Y are going to be in units of dollars, and that means we're going to yield a system. This thing yields a system of dx dt and dy dt, right? Those two differential equations are buried in this one matrix equation. And of course, if X and Y are in units of dollars, because it's profits, then that means dx dt and dy dt would both be in units of dollar per time, dollar per day, dollar per hour, probably day, given that it's daily profits. So we can take a look at this context. There's plenty of context that you can read about on page 291, but the coefficients tell us how the daily profits for both stores affect the change in profits of each of the stores individually. In other words, the dx dt equation, the top equation, would be negative 2x minus 3y, and the dy dt equation would be negative 3x minus 2y. And so you might initially take a look at this and think, wow, everything's negative, all the coefficients are negative, so that must mean falling profits always and evermore. Well, not necessarily, and so we're going to take a look at this, and we're going to solve this system. We're going to use Maple to solve the system. And literally, I'm just going to say, using Maple to solve the system, we can find lambda 1 and lambda 2, and their corresponding v1 and v2. And so if you take a second and write this into Maple and have Maple find the eigenvectors for those, you'll get the eigenvalues and the eigenvectors, and you find out one of the eigenvalues is negative 5, and it corresponds to with a eigenvector of 1, 1. And the other eigenvalue is positive, it's positive 1, and it corresponds with the eigenvector negative 1, 1. And so this, if you kind of imagine what that would look like on the phase plane, this is really the line y equals x, right? And whereas this one really corresponds to y equals negative x, right? So if you try to imagine what our phase plane is going to look like, there's two straight line solutions, and the straight line solutions are in these two directions. And if we go one step further and say the straight line solution that is along the y equals x line should be headed towards the origin. So everything should be pointed kind of towards the origin along that line. I'm like doing pantomime underneath the camera like you can see it. And of course the other one, the one that's following the y equals negative x line, is going to be positive, so we would expect to see things moving away from the origin along that line. So towards the origin in this direction and away from the origin, and that means, of course, one's positive, one's negative. We would expect it to be a saddle, right? We expect it to be a saddle since one lambda is greater than 0, right? In that case, lambda 2, and 1 lambda is less than 0, and that's lambda 1. So since we have two different signs on our eigenvalues, we know that we're dealing with an origin that is a saddle point. And if we wanted to write out our full solution, our general solution for this, we would get something that looks like this, and get our big y of t going on, and that's going to be equal to k1 times e to the, I'm going to borrow for lambda 1, negative 5t times its vector, which is 1, 1, plus k2 times e to the t, just 1 times t, times its eigenvector, which is negative 1, 1. And that's the general solution. Now, you can clearly see the straight line solutions at play here, right? So you can see there's a straight line solution number 1 and straight line solution number 2 right there, kind of embedded in our general solution. And so the general form, when it's in matrix form, allows us to see pretty quickly and easily what those straight line solutions are, and we can kind of visualize what the phase plane would look like. But in order to talk about kind of making predictions and making sense of what's going on in a kind of a practical sense, we want to be able to convert this into another way of thinking, which is in terms of x and y. Because of course we want to be able to make predictions for what happens to the profits for the coffee shop and what happens to the profits for the tea store or tea shop. Is there such a thing as a tea shop? I suppose there is. So in order to do this, we're going to kind of play out our equation, kind of follow it along on the top to get our x equation. So it's just going to be k1e to the minus 5t times 1 plus k2 times negative 1. So it'd be minus k2e to the positive t. And then y of t down here, following the bottom of things, will just be k1e to the minus 5t plus k2e to the t. Now, on first glance, you might look at it and say, okay, well, you've got, for x, you've got exponential decay and exponential growth, but there's a negative there, so what does that mean? And for the y of t, you've got exponential decay and exponential growth, but it's positive, so they're different. They're fundamentally different. But what does that mean in terms of making predictions? Well, we really can't make any predictions without any initial conditions. So without initial conditions, we can't really make predictions. But what we can do is we can think about things qualitatively. And so we're going to take a look on the next page what happens when you take a look at the phase plane. And I went ahead and created a graph that has both of those two straight line solutions appearing on the phase plane. So at the top it says, egad, what's it all mean? So here's a picture of the phase plane. Here, I'll just leave it like that. It's a picture of the phase plane with my two straight line solutions. And so if we're kind of paying attention to what's going on with the two straight line solutions, you can imagine one of them, since they're already kind of colored in, see if I can use a highlighter here and make it a little bit clearer. We've got this straight line solution that kind of runs along this line, y equals x. And we saw that one. That's the one that's associated with lambda equals negative 5. And then we have the other, which runs kind of perpendicular to it across the origin. And that's the one that's associated with lambda equals 1. So what are we looking at here? Well, without being able to have a specific initial condition, we really can't make much predictions other than things are going to tend to follow this line away from the origin, and things are going to tend to follow this line, straight line solution, towards the origin. But when you venture out into the phase plane, not on those straight line solutions, you discover some interesting things happen. So one of the things that you might kind of pay attention to is the fact that everywhere in quadrants, or not even quadrants, everywhere above this pink line, if you want to think of it like that, everywhere in this region, all of the initial conditions in this area, what's happening here? If you're an initial condition in this region, right? So pick a point anywhere. So I'll choose a point like right here and say, well, what happens to the solution curve over time. Well, you can follow the slope field essentially, and kind of and see what happens to this curve, and then eventually it's going to get close and kind of get kind of sucked up and follow along that path. And so what you're seeing here is if you start anywhere in this region, anywhere in this yellow region, whether it's over there or up here, you can kind of do the same thing with a solution curve that might go something like this. No matter what you do, if you start in this yellow region, it's going to wind up meaning your x, the x coordinate, is going to approach negative infinity because you're heading in that direction, and your y coordinate is going to be approaching positive infinity eventually. Notice it doesn't happen right away. Right away the x coordinate is decreasing as I'm going this way. The x coordinate's decreasing, but the y coordinate's decreasing as well. And then we reach this point somewhere down here where all of a sudden the y coordinate starts to increase, and you wind up with a solution curve that's describing x coordinate is continuing to decrease while the y coordinate is increasing. So what does that mean? That means that the coffee shop, remember that's x, loses money. dx dt is less than 0. But the tea shop eventually gains money. Gains. Now notice I say eventually because in the case of this point right here, the tea shop doesn't start off gaining money. It starts off losing because the y coordinate's going down. Just like over here, initially the x coordinate is increasing, but I suppose I should write eventually here. Eventually. There we go. Loses money, but the tea shop eventually gains. So, and this grows, without bound in both of those directions. And so this general direction for all of our solutions is telling us that x is going to become more and more negative, meaning lower and lower profits, but the y is increasing more and more profits, right? So as t approaches infinity in this region over here, x is going to approach negative infinity and y is going to approach positive infinity. And so that means if you are the coffee shop, then you don't want to be in this region. You don't want to have an initial condition in this region. So this region is bad for coffee, but good for the tea store or the tea shop. But what about the other side? What about everything on the other side of things? Well, you're probably not going to be surprised to find out that there's a slight difference over there. So I'm going to try not to blanket it with too dark a highlighter, but this whole region over here, everything over here is a different story. If you start off, notice we could start off with the exact same x coordinate, but a slightly different y coordinate. Let me grab a pen here that can actually show up. And following that curve, we see a pattern that flows in that direction. If you started with something over here, they seem to both be headed out that way. And so what does that mean? Using our lens of coffee shop and tea shop. In both of these cases, if you're in this region over here, an initial condition in this region yields eventual profits for the coffee. And of course that's because eventually the x is going to increase. So notice right at the start the x decreased, but as we start going this way, the x-coordinate is getting bigger and bigger and bigger, more positive, but the y-coordinate is decreasing. Okay. Eventual profits for coffee, but eventual loss for the tea store. So whether you start an initial condition up here or over there, or around here, you wind up with the problem of it's bad for the tea, but good for the coffee, right? So we would say in this region, it's bad for tea, good for coffee. And kind of following the same pattern that we did up here, the reason that we say that is every single one of these solution curves is saying that as t approaches infinity, and remember, t is neither of the variables on this. T is just playing it forward in time, what happens over time. Well, if you start here over time, you're going to follow the field values. So as t approaches infinity, x will eventually approach positive infinity, while y will eventually approach negative infinity. That means bad for tea, but good for coffee. It is worth noting that this is what we call a competitive system, right? The tea and the coffee are competing with each other. And so this idea of is a competitive system always a bad thing? Or could it ever be good for both? Well, by definition, a competitive system, this is what we call a competitive system. And by definition, a competitive system can only be good for one, but not both. And the way you can think about this is the kind of the idealized simplest cases are, sorry, I'll try to leave that on the screen. The simplest cases are if you're on these straight line solutions, if you're here or here or here or here, what's going to happen? Well, if you're along the pink line, you're going to head towards the origin, whether you're up here or over there, whether you start off with high profits, high daily profits for X and Y, or you're in the hole for X and Y. Either way, your profits are going to go to zero. Or if you're along this line, if your initial conditions are along that line, then you're going to wind up taking off forever that way. The only situation where things wind up reaching an exact perfect equilibrium is if you happen to be exactly on that pink line. So I'm going to make a little kind of special note here. The special case. When the initial condition is on. And let me do straight line solution number, I can't remember, which one was that? Was that number 2? Oh, I'm going to have to look at it real quick. Which one was it? Straight line solution number 1. That was number 1. If it's on straight line solution number 1, then all profits head to 0. They don't go to negative infinity or positive infinity. They just go to 0. They head towards the origin. But that's a really special case, right? And so in this case, you might think, well, is it possible for a coffee store and a tea store to both succeed in a community, both succeed in a particular place economically? And if the answer is yes, then whatever model you use to come up with this doesn't predict that. It's not possible, according to the model that we have, that there's success for both. So if you're dealing with a competitive system, but you're modeling a real life situation that's not purely competitive, then you might have a situation where the common sense needs to kick in. And so at the bottom, I have a little quote there that says, although it's always wise to compare the predictions of a model with common sense doesn't replace computation. Models are most valuable when they predict something unexpected. So from the previous page, we might have expected it's dire consequences for everybody. The tea store and the coffee store, they'll never succeed. But that's not what our model predicts. Our model actually shows that it's quite possible for the tea store to do just fine. It's quite possible for the coffee store to do just fine. It's just not possible for both. Why does it say but not both both? I just realized it says not both both. Ignore that second both. So that gets us to the end of 3.3. So hopefully you can make sense of those problems on the problem set for 3.3. And we'll check in next time with 3.4.